All right, let's take a look at this inductive circuit. And we want to calculate the total inductance, the inductive reactance, and we're going to go ahead and break this down and get the Q bar for each of the inductors as well. So if this was a resistive circuit, well, what we would do is we would simplify it. And so we would simplify it into something like this, where we would have, 120 volts over here, and then it would go to a reduction right there, where these two that were in parallel would become that one right there. And then because these two were in series, we would get a further induction here, or a further reduction here into a single one like that. Okay. And then we could get all our numbers and work it backwards. And so we're gonna do it that way. But in order to do it that way, we have to get the inductive reactance of each one of these, and then kind of our rules that we learned for Ohm's law and for our resistors in series and parallel apply. So let's go ahead and do that first by getting the inductive reactance here. So we know that our inductive reactance, XL1, for example, would be 2 pi FL of that inductor. And so that first one right there, our XL1, 2 pi F is 377 times 6 henries. And then these two right here, XL2, and they're 1 ohm, so they're both the same, are going to be 377 times 1 henry. Okay? And so that is going to give us our inductive reactance for each one of those. So if I went 2 times, we're just doing 377, sorry, 377 times 6, I get, oh, that doesn't look right, let's try that again. 377 times 6 equals 2262 ohms, and if you go through 2262 ohms, sorry, and 377 times 1 is 377 ohms. Okay, so that's where we're ending up. So we labeled these here. This would be 2262 ohms, and I'll put it here, 2262 ohms. And these ones right here, these are 377 ohms, and this one right here is the same, 377 ohms. All right, so when we move to a reduction here, when we learned about resistors, when they were in parallel, the reciprocals of these added, and then we took the reciprocal of that. Well, now that we've got our inductance here, we can use that same thing. So in order to get this one right here, we would go 1 over XL T equals 1 over XL1 plus 1 over XL2, which is going to be 1 over 377 plus 1 over 377, and then we'll flip it, right? So if I go 377 and then I flip that, I get 188.5. So that's what this one is going to be here. That is the reduction of these two into this one right here, gives me 188.5 ohms. Okay, then to get this one here, well, these are series, so they would add. So we would get, XLT equals XL1 plus XL2, which is going to be, 2262 ohms plus 188.5 ohms. So if I take that and I add 2262, I get 2450.5 ohms. So this right here is 2450.5 ohms. Okay. So because I'm converted this inductive reactance to ohms, all my rules in my power wheel, it's a modified power wheel. I'm not using resistance anymore. I'm using XLT. That's going to work. So if I go right here, I can go ahead and I can get my current for the entire system right here. So I can get I equals not V over R, it's V over XLT, which is going to be 120 volts over 2450.5 ohms. And so if I get that, 120 divided by 2450.5, I get 0.049 amps. So this is 0.049 amps. And I know over here that my I total is 0.049 amps. Okay. And I also knew that my XLT total right here, XLT, my total was 2450.5 ohms. Okay. While I'm over here working on this, we know that my my power is VI, but remember, we're not using power. We're using QVAR, which is going to be V times I. Okay, so my total over here, instead of power V times I got QVAR V times I, is going to be 120 volts times 0.049 amps. So I take this times 120, I get 5.876 VARs. Okay, so my QVAR is 5.876 VAR. Okay, so now it's just like we did, we learned before. We kind of work it backwards right here. So what can I do right here? Well, on this one, I've got my voltage and I've got my current and my resistance, because this is just 120 volts right here. So when I back up, I see that this is in series. So in series, the current stays the same. So I'm bringing this 0.049 amps to each one of these. Okay, it's because current stays the same. Recognizing that this is the same right here, for this one, I've got my 0.049 amps. That stays the same. Okay, but this is the simplified simplification of these two in parallel. So what do I know? That in these, voltage stays the same, so it looks like I need to get my voltage right here. Okay, so what is my voltage for these right here? Voltage, V equals I over R, but we're not using R, we're using V equals I over XLT. So if I get my current, 0.049 amps over 188.5 ohms, I get 0.049 divided by 188.5 equals a pretty small number there. Looks like I'm got a little bit something going on. Oh, V equals I times R. I'm a little ahead of myself, sorry. V equals I times R. So in our case, sorry, it's not R, it's XL. There we go, my bad. So let's try that again. We would have 0.049 amps times 188.5 ohms. Oops. So we're going 0.049 times 188.5 equals, is that right? 9.237 volts. Okay, so this right here is 9.237 volts. Okay, so when I back it up, I go from my reduction back to here. It's parallel. What stays the same? 9.237 volts. So this is 9.237 volts, and this one is 9.237 volts. There you go. Okay, now I can get these right here. I equals V over R, but we're not necessarily doing that. We're using reactance. I equals V over XL, which is going to be 9.237 volts over 377 ohms, and that is going to be 1 over X, no, let's do 1 over X divided by 377 is 0.0245 amps. And so this one right here is 0.0245 amps, and this one here is 0.0245 amps, just because they're both the same rating there, okay? And that makes sense. It looks like 0.049 amps, it has to get split. It looks like half of that is that and half is there, and those add up to that, so that's looking good. And so you can work through here. You can get your Q bar for each one of these, for example. You can get, let's get our voltage here first. We need voltage for of L1, and that is I times R, not our XL. We're looking at 0.049 amps times 2262 ohms equals, let's do that, 0.049 times 2262 is 1110.84 volts. This is 110.84 volts, and that looks about right, 110. And then these drop the same, 9, so you add those two together, 110 and 9, and some change, and you get 120. So that's making sense. And then we just need to get our Q var for each one of those. Q var of 1 and Q var of 2 and 3, which are going to be the same because they're the same numbers, is going to be V times I, which is going to be my voltage here, 110.84 volts, and these voltages were 9.237 volts. The current here was 0.049 amps. The current here was 0.0245 amps. And so you multiply those together, you get 110.84 times 0.049, giving me 5.431 Q var. And then these ones right here are going to be 9.237 times 0.0245 equals 0.226 Q var. That looks the number a little bit low. Let me just check that again. 9.237 times 0.0245 equals 0.226 Q var. And remember, they're the same here, 0.0226 Q var, 0.0226 Q var, and this one was 5.43 Q var, or 31 Q var, okay? And so my final check is my total Q var was 5.87. Well, that 5.87 should be the 5.4 plus the 0.02 and the 0.2, so yeah, it's pretty close, or 0.22, it should be the 0.22, got missed a decimal there. So yeah, 0.2, 0.2, and 5.4 gives me about 5.8. So basically, once I've got my inductive reactance using the formula right here, I kind of just treated it like a combination circuit for resistance, a resistive combination circuit. I subbed in, instead of using resistance, I used XLT. So that's the solution there for that.